Thank you for listening to my talk. In this talk, we're going to study holonomic sequences, which are sequences for our purpose of real numbers that satisfy a linear recurrence relation with polynomial coefficients. For this reason, they're also called p-finite, let's say with real polynomial coefficients. The most familiar example of such sequences are those with these polynomials such as constant functions, so we just have constant coefficients. Then we get linear recurrences or C-finite sequences such as the Fibonacci sequence. But of course, holonomic sequences with non-constant polynomial coefficients are much more versatile and powerful. You can express things like factorials, binomial coefficients. The Catalan numbers are a special case, and they can be characterized essentially as the Taylor coefficients of formal solutions of homogeneous linear ordinary differential equations with polynomial coefficients, which makes them show up in many applications in science and such. They are effectively closed under addition and multiplication and other operations, which implies that the equality relation for such sequences is decidable. And this is quite a powerful tool for automatic equality proving. So to give an example, say we wanted to prove the familiar equality sine squared plus cosine squared is equal to 1 for all numbers on the complex plane. We could do so by observing that the Taylor coefficients of sine squared, cosine squared, and 1 satisfy a fourth order holonomic recurrence, which is induced by this ordinary linear differential equation, which implies that sine squared plus cosine squared minus 1 satisfy the same holonomic recurrence. And so we just have to compute the first four Taylor coefficients of this function and check that they're all 0, and we show that the function is identically equal to 0. So seeing all this, it's very natural to ask, can we test such sequences for inequality as well? This in turn leads to a decision problem that is known as the positivity problem. So given polynomials with integer coefficients, the leading polynomial non-zero, and initial values, say rational numbers, are all terms of the sequence that satisfy this polynomial linear recurrence non-negative. Now this has been studied for constant coefficients quite extensively, so for C-finite sequences. It's not known to be decidable for all orders, so the number r is usually called the order of such a sequence. It's only known to be decidable up to order 5, and there's strong evidence that a decision method for order 6 or higher would constitute a major breakthrough in Diophantine approximation. By contrast, in the case of non-constant coefficients, rather little seems to be known. To our knowledge, there's essentially one algorithm due to Gerhold and Cowers based on cylindrical algebraic decomposition for solving the positivity problem in practice. It's a partial algorithm, so it doesn't hold on all inputs, and there exist sufficient determination criteria for second and third order recurrences where the outermost coefficients have the same degree and all coefficients in between have at most that degree. So in our work, we're approaching the problem more from a theoretical computer science perspective, trying to identify decidable instances of the positivity problem. So we consider a very simple class of holonomic recurrences. Recurrences of the form f of n plus 2 is equal to p of n times f of n plus 1 plus q of n times f of n, where p and q are integer polynomials, non-constant, the degree of q smaller than or equal to the degree of p. This is arguably the simplest class for which the positivity problem is not completely trivial. So we obtain the following results. We get a complete classification of the possible asymptotic behaviors of these sequences. And as kind of a corollary to this classification, we get a partial algorithm that decides positivity for almost all initial values. And by looking a bit more closely, we get certain subclasses of these recurrences for which our algorithm is either already total or can be extended to a total one. These subclasses we can algorithmically recognize as well. Let me start with the classification result, which is really the central result of this work. In order to motivate this, I'll show you a simple example. Let's consider this very simple second order recurrence with linear terms. F of n plus 2 is equal to n minus 1 times f of n plus 1 plus n times f of n. For this, we can find an explicit closed form solution, which I've written down here. It has an alternating bounded term, and it has a term where we have this alternating sum involving factorials and this term involving a factorial. And if you stare at this for a bit, you'll notice that in the second term, the first summand here is going to dominate the sum eventually. So the coefficient of f1 plus f2 halves is going to be positive. And since the first term here is bounded, this means that if f1 plus f2 does not vanish, then the sign of the sequence will be eventually equal to the sign of f1 plus f2. Meaning that if f1 plus f2 is positive, then the sequence is eventually positive. If f1 plus f2 is negative, then the sequence is eventually negative. However, if this term vanishes, f1 plus f2 is equal to 0, then we just have this term, this alternating term, and then our sequence degenerates to a first order recurrence. F of n plus 1 is equal to minus f of n. And now it just depends on the value of f of 1. If f of 1 is equal to 0, then our sequence is equal to 0. If f of 1 is positive, the sequence will alternate in the pattern plus minus plus minus plus minus. If f of 1 is negative, it will alternate in the pattern minus plus minus plus minus plus. So if we think of the possible initial values as points on the Euclidean plane, then we get a line that divides the plane into two open half spaces. Above the line, the sequence is eventually positive. Below the line, the sequence is eventually negative. The line itself is two pieces where on one piece we're alternating in the pattern plus minus, on the other piece we're alternating in the pattern minus plus, and these pieces are separated by the origin with a constant equal to 0. So we get a complete picture of the possible asymptotic behaviors as functions of the initial value, so to speak. And our main structural result is that this picture we will get for any sequence of this type. They cannot be more complicated than this. So to state the result more formally, let's assume we're given such a recurrence, and let's first bring it into a certain normal form. Let's assume that P has a positive leading coefficient, that P and Q have no positive real zeros, and for technical reason that this discriminant P squared plus 4qn is strictly positive for all positive integers. This can always be achieved for any recurrence of this type, simply by shifting and scaling the recurrence. Of course, for the fourth item to hold true, it's important that the polynomial P be non-constant, but then by the assumption on the degrees, it can always be achieved. So once we have normalized our sequence in this form, if we look at the space of initial values, we get the exact same picture as we saw before. So we have the plane, it is separated by a line into two pieces, h plus and h minus. On h plus we're eventually positive, on h minus we're eventually negative. The line itself is separated by the origin into two pieces. Let's call them L plus and L minus. And on L plus we're eventually positive or alternating. On L minus we're eventually negative or alternating. And whether we're alternating or have constant sign on the line depends on whether the polynomials have equal sign leading coefficients or opposite sign leading coefficients. We are alternating if and only if they have equal sign leading coefficients. In the origin, got constant equal to 0. Moreover, we can compute the slope of this line as a continued fraction expansion. So the slope will be equal to minus this continued fraction expansion involving Q and P. So this is just a notation for this type of continued fraction expansion, which we can effectively compute. Now from this we get, essentially from the proof of this, we get a computational corollary. If we are given a recurrence in normal form, rational initial values, and moreover the information which of the 5 pieces that we've identified we lie in, we can, because our proof is sufficiently constructive, compute an index n such that the signs of the sequence where you start from n are as prescribed by the piece. So you either have constant sign, you're alternating, or you're constant equal to 0 depending on the piece which contains the initial values. So if you have this information, which piece you lie in, and an index from which point on you behave as prescribed by the piece, you know everything there is to know about the signs of your sequence, and you can answer all sorts of questions about your sequence. In particular, you can decide the positivity problem. Of course, this computational result is not quite satisfactory, because in practice we would be given the recurrence, we would be given the initial values, but we would not be given this information. This information we'd have to compute ourselves. So the next question is, can we compute this information? Well, let's see. So again, let's assume we're given a recurrence in normal form and initial values, rational numbers. Well, clearly we can decide if the initial values are both 0, so if we're in the origin. Also, since we have this continued fraction expansion for the slope of the line, we can numerically approximate the slope to any given finite accuracy, which means we can always test if we're off the line. So we can semi-decide if we're in this positive half plane h plus, or we can also semi-decide if we're in this negative half plane h minus. But unfortunately, in general, we do not know how to decide if we're precisely on the line. So we only get a partial algorithm where the algorithm halts whenever we're not on the line and produces, say, the correct answer for the positivity problem. But if we're on the line, the algorithm will run forever. Now there are cases where we can do better. So recall that the slope of this critical line was given by this continued fraction, and the problem is, of course, we do not know how to decide whether this quantity is equal to a given rational number. But there are two good cases in which we get a total algorithm anyway. If the line does not have rational slope, if this is not a rational number, then there can't be any non-trivial rational numbers on this line other than 0, and 0 is fine. And so our algorithm will happen to be total. There will also be cases where we can compute this number explicitly as a rational number, in which case we can compute the slope of the line, and we also get a total algorithm. I will say more about this later. We have criteria that ensure that the slope is irrational and that ensure that the slope can be computed as a rational number, but these will require some ideas from the proof. Okay, let me move on and briefly try to explain how to prove the main result. And the basic idea is very simple. We essentially follow the proof of the decidability of positivity in the C-finite case, where a natural answer is to say we consider the companion matrix of our problem. It's a matrix that, unlike in the C-finite case, is a function of n. It takes the nth and n plus first term of the sequence and produces the n plus first and n plus second term, so that we can express the vector containing the nth and n plus first term as taking the first and second term of the sequence and applying this matrix product. This matrix has two distinct real eigenvalues because we assumed that the discriminant here is strictly positive. So it has an eigenvalue that we call lambda 1 of n. This will be a large positive real number approximately equal to p of n, and an eigenvalue lambda 2 of n, which will be a small real number, could be positive or negative. It will be approximately equal to some constant, and it will converge to a constant. Now, since the matrix has two distinct real eigenvalues, it will be diagonalizable. Again, with a diagonal matrix depending on n and base change matrices depending on n. So more explicitly, we can take the diagonal matrix to be the matrix where lambda 2 is here, lambda 1 is here, and then we have base change matrices depending on n, whose entries depend on the eigenvalues evaluated in n. Now, based on this diagonalization idea, we can try to compute this matrix product. Let's say we start at index k, being prepared to drop finitely many terms of our sequence, and we want to let n essentially go to infinity and try to compute this matrix product to get something like a closed form expression of our sequence. Now this matrix product, it will be something that's kind of sandwiched by the nth and kth base change matrix here, and the main contents of this matrix product will be that we have products involving a diagonal matrix, and then these expressions of the form Sj inverse times Sj minus 1. In the C-finite case, the base change matrices don't depend on J, so that this expression is just equal to the identity. In our case, of course, the matrices depend on J, and this will not cancel out, but this expression will be approximately equal to the identity. So for large K and N, this expression will converge to the identity. So this leads us to the ansatz to say, let's introduce for these expressions error functions that depend on J, that tell us how far off we are from the identity. And then as a second ansatz, let's just give names to the entries of the matrix product, let's say sandwiched by these base change matrices. We obtain, by elementary linear algebra, recursive linear equations for the entries of this matrix. And I don't expect you to parse these equations in detail. Just note that for each matrix entry, we get a linear equation in terms of the previous matrix entries that has coefficients that involve the eigenvalues and these error functions. And also note that A and B involve the small eigenvalues, and the equations for C and D involve the big eigenvalues. And now the main work you have to do is to show that you can relate these quantities given by these recursive equations in a meaningful way. So more precisely, we're going to show that there's no cancellation in the recursive equation for dkn. So dkn is strictly positive for large n and k. And akn divided by dkn will converge to 0 as n goes to infinity for each fixed k. Likewise, for bkn divided by dkn will converge to 0 as n goes to infinity. Now, the sequence ckn divided by dkn will always converge to a limit L of k when we fix k and let n go to infinity. L of k will not necessarily be equal to 0, but it will converge to 0 as k goes to infinity. So this is the actual main content of the proof. Unfortunately, I can't really show you any of this in the restricted time that I have. In fact, we need a slightly stronger result than the one that is stated here. We need a quantitative version of this, where we also elucidate the rates of convergence, not just the fact of convergence. But for the proof sketch, the qualitative version will have to suffice. So once you have this, the rest is simple algebra. So we can express the nth and n plus first term of the function in terms of these base change matrices, the functions that we understand now by the main lemma, and the kth and k plus first term of the sequence. So we get an explicit equation for f of n multiplied with, say, lambda 1 of k minus lambda 2 of k. You don't have to pass this whole expression, but it's a linear combination of the initial values f of k plus 1 and f of k, involving these functions a, b, c, and d, and involving the eigenvalues. Now we can divide this by d and go to the limit using our main lemma, and then we get a linear expression in the initial values f of k and f of k plus 1, involving the eigenvalues and this number L of k, which is the limit of c of k(n) divided by d of kn. Now on the left hand side here, we have lambda 1 of k minus lambda 2 of k, which is a positive number because lambda 1 is the large eigenvalue, and we divide this by d of k and n minus 1, which is also a positive number. So the sign of the left hand side is always equal to the sign of f of n. So if the right hand side doesn't vanish, we're immediately done. Yeah? If the right hand side is strictly positive, then the sequence will be eventually positive. If the right hand side is strictly negative, then the sequence will be eventually negative. However, of course, if the right hand side vanishes, we don't quite know what happens yet. So we have to look a bit closer. Now, of course, the right hand side was a linear form in f of k and f of k plus 1, so it defines a line lk in the f of k plus 1 plane, and it's a relatively simple observation that the matrix M of k maps the kth such line onto the k plus first such line, so that if you're once on the line, you're on similar lines forever. So from the kth index on, you will satisfy a first order recurrence, as we've seen in our very first example. Our recurrence degenerates to a first order recurrence with a coefficient that depends on the eigenvalues in this number L of n, but by the quantitative version of our main lemma, this expression will be approximately equal to lambda 2 of n times f of n. And then we essentially get our result. The sign of the sequence will be constant 0 or alternating, depending on the sign of f of k and the sign of lambda 2 of n. I should mention here, the sign of lambda 2 of n is constant. It will either be positive or negative. It will never change sign, so this makes sense. So we get the case alternative that we saw in the beginning. We have 5 cases. Either we're in one of two half spaces where we're eventually positive or negative, or we're on a line, and depending on what our initial values do and what our eigenvalues look like on the line, we will be positive or negative or alternating, and in the origin we will be 0. So we get the picture we saw in the beginning, now in the f of k plus 1 and f of k plane, but by assumption our matrices were non-singular, so we can just take the matrix product, invert it, and transport this picture back onto the f of 1 and f of 2 plane, so that we get the announced result and the announced picture for any recurrence. I should also say, I won't go into details, but we said that the slope can be given by a continued fraction expansion. This you can also see by observing that the kth companion matrix maps the kth line onto the k plus first line and doing some simple algebra. So finally, let me address the question in which cases we get a total algorithm. Before we do this, let me just reduce the coefficients of p and q a little bit. Let's say we write a0 to ad for the coefficients of p, b0 to bd for the coefficients of q. As always, we assume that ad is strictly positive, but now let's assume that there's no prime number p, which divides all the a's, such that p squared divides all the b's. This can always be achieved by scaling the sequence and ensures that the coefficients are as small as possible. So under this assumption, let's study the cases in which we can find the total algorithm. So if the critical line where we cannot in general decide positivity has a rational point, then it has an integer point, and we know that the points on the critical line will satisfy this first order recurrence, which approximately is just multiplying by lambda 2 of n. Now the function lambda 2 of n is either positive or negative, it can never change sign, and its derivative also can never change sign. It's either constant or strictly increasing or strictly decreasing. Also, lambda 2 of n converges to bd divided by ad as n goes to infinity. If lambda 2 of n is a constant function of n, then it turns out that L of n is always a constant equal to 0. So this approximate equality becomes an actual equality. We can just keep multiplying with lambda 2 of n when we're on this line. And it will follow that the slope of the slope of the line is equal to lambda 2 of 1, which has to be a rational number in this case, and we can of course compute it, and we can test if lambda 2 is a constant function, then compute the slope of the line, and then we get a total algorithm. So that's one instance where we get a total algorithm. The other type of instance where we get a total algorithm is when the slope of the line is guaranteed to be irrational. So when this recurrence does not have any non-trivial integer solutions. And the first observation that we make is a very simple one. If the degree of q is strictly smaller than the degree of p, or the leading coefficient of q is strictly smaller in magnitude than the leading coefficient of p, then we cannot have non-trivial integer solutions, because lambda 2 of n converges to bd divided by ad. The recurrence is such that we essentially multiply by lambda 2 of n. So eventually we would be multiplying with numbers strictly smaller than 1, so that we converge to 0, but if we're an integer sequence that converges to 0, we have to be eventually equal to 0, but the only sequence that is eventually equal to 0 by our classification theorem is the constant 0 sequence, so we cannot have a non-trivial integer solution in that case. And while this observation is very simple, we can push it a little bit to get a slightly sharper result. If the degrees are equal and the leading coefficients are equal in magnitude, then we can still, under some assumptions, prove that there are no non-trivial integer solutions. Namely, if lambda 2 is negative and decreasing or positive and increasing, meaning that it either converges from above to -1 or from below to 1, so it's always bounded by 1 in magnitude, in which case the sequence would have to be bounded. Or even if it's positive and decreasing or negative and increasing, so it is greater than 1 in magnitude, converges from above to 1 or from below to -1. And a somewhat technical condition on the coefficients is satisfied. The d minus first coefficients are controlled by the degree and the leading coefficient. In that case, lambda 2 of n will converge sufficiently fast to 1 in magnitude so that we can get a bound on the growth of this sequence, and we can show by a height argument that no integer solution to this recurrence equation can grow so slowly, and then we also find that there are no non-trivial integer solutions. So to wrap up, we've achieved a classification of possible asymptotic behaviors for a very simple class of holonomic recurrences. This yielded essentially a partial algorithm for positivity that holds almost everywhere, and we've identified some effective criteria where we get a total algorithm. In future work, we'd like to generalize this to third order. This seems doable, but would be a little bit more complicated. So thank you very much for listening to my talk.